Audio check 1, 2, 3. Audio check 1, 2, 3. All right, sounds like we are up and running then. Ladies and gentlemen, welcome to the stream of the Discourager of Hesitancy. We are working on a game with no game engine, and today we are trying to fix up the QOI image encoder so we can, well, decoder, so we can test the QOI image encoder. You gotta be able to do both operations. So that is the plan. We got most of the code written. It's just figuring out where we're wrong. And as far as overall flow and process, I think it's correct. So it's things inside that, possibly RGBA ordering issues, misunderstandings. It'll be fine. We'll work it out. But we're gonna have to debug that. And hopefully we can get that done. We'll see. We'll see how long it takes us to get it done. I'd like to get this done today. We will see. We will see. So yeah, we were just testing the QOI image, encoding and decoding. Well, I think we're just on the decoding part right now. Ooh. Oh man. Stayed up late last night dipping caramels. So I made homemade caramel, and then you cut it into squares and you dip it in good quality dipping chocolate. It is so good. So I'm going to be eating some of that. Trying to think if there's anything I should bring up before we go crazy. I don't think so. I think we're good. Ooh. All right, so let's go into yield journal. Blah blah blah. I'm good. PNG should for the size. Start QOI decoding test, which I will say we did. Put up the QOI decoding test. Not working right. Needs debugging. Number of pixels in output is correct so far. Just the colors are wrong, and I probably need to. Yeah, that's probably good enough. Okay, then get our tasks and notes for the day lined up. The 19th, 6 days till Christmas. I probably won't stream Christmas Eve or Christmas Day. Too many family activities. And then we'll have to see what's going on after that. Oh man. So we need to start off by debugging QOI decoding. Then we need to implement QOI encoding. Then put QOI encoding into embed PNGs. Then put QOI decoding into image warehouse, texture store, somewhere around there. Somewhere. Okay, that's basically it. So, if there's any questions, let me know. Otherwise, we're going to start in on the debugging. Probably should save our work at this point. I'm not sure what I want to keep and what I want to throw out yet. I want bitmaps. Test QOI. I'm fine with that being there. So, what we really need done is not hit ignore. Start.bitmap. Yes, I've been working a little bit in the background on the plants, but honestly, not much time these days with the holidays coming. So nothing there to show, really. Started implementing QOI decoding, needs debugging. Good enough. That way we have a safe place to come back to. So, when I say I'm testing, there was a download pack that came with, well, that's on the QOI website. And if I, this file exists as both a PNG in that folder and as a PNG and a, what is this? QOI image format. So I'm reading in the QOI version of this image, and then I'm trying to output this as a bitmap. And this is what we're seeing so far. Pops up, there it is. So, I've seen worse. I've seen better. We'll just have to see. So this basically exercises all of our color and alpha channel stuff. Gives you some gradients, different colors. So we want to put out something that looks like this, but we're getting this. So that's the debugging thing we're doing today. Which is good, because I think while we generally understand the specification, which is very simple, by the way, like, let me just throw up the link to that, because it's, like, specifications should be written like this. I'll go ahead and put this in and pin it. Yeah, this is a great format, as far as I can tell. Even if it's not as efficient in space usage as PNG, like, I can code this up myself. It's small enough. Encoding, decoding, plenty fast. That caramel is so good. Okay. So I think we're ready to get started. When we run this file, we get the right image size. The QOI loaded, we got the right image size. The input was 20, let's see, where is it? 22 kilobytes, that's about right. The output we would expect 65,536, which is correct. We test the equivalency of what we expect and what we actually parsed out, and that's correct. Well, what we decoded into, so those match. But what we're not seeing. Let me bring up the actual QOI file in hexel mode. So here's the magic number. Then we get our size. This is 256. This is 256. We get 4, which is the number of color channels in this image, which doesn't change the rest of the format. It's basically a note to the person who's reading the image. It doesn't affect the actual format. And then the 0 says this is an sRGB, not a linear color image. And again, this byte has no effect on the rest of the format. Then we start in on the actual file format. What we do is we read in a byte. Get our width, we get our height. Then we're done. So we load our QOI. This is our QOI data. Well, that's the full file buffer. Then we say decode. Then we take the decoded stuff, write it out to a bitmap. Okay, so decode is where I think we have issues. We assert certain things. Create our results buffer. We have a current color, which we always maintain at, well, we start with 0, 0, oh, not 1, 255. Shame on me. These are bytes. Then we have a 0 filled color array. You read a byte. And our first byte is 5, 5. Kind of surprises me, but oh well. Ugh. I think we're going to log things like this. What are we going to do like this? Bool log equals true. Log equals false. inside here. If we've done 10 pixels, we do that. Okay. Log note. So this is our pixel number, right? Modulus D. Here's our opcode. Modulus 3U. That will be current.red, current.green, current.blue, current.a. If we get RGB out of that one, FE. So this is index. Look up index. Index. Difference, though, that's kind of an interesting one. The diff, we start with pixel index. 3U, oh no, 3D. This 3D. Change in red, delta green, delta blue. And then the current color, and we're done. Luma, I honestly, this one is the least clear to me. DG, DRDB, and then current, and then run. Of the current color with no modification to that color. And that's basically it. So we just want to see what the instructions even look like. Now a 5 is a 1, 0. It actually means 1, 0 according to this spec. It starts right off with the Luma byte. We can obviously print more stuff. Let's just see what we get here. Oh, no. Yeah, test card. We want the test card RGBA. This one. So let me drag that over. Put that in hex mode. Size for the color space is sRGB. Now we start with an FF, which should then be red, green, blue, alpha. So first thing you get should be an RGBA, red, green, blue, all the way up, 0 alpha. So basically an full alpha white. Then an FD, and F is 1, 1. Therefore, we expect the second thing to be a run. That run is 200, well, no. A run, F, run of some number. If I have FD, this is the run. FD is the run. So, what is FD in bytes? I need a calculator. I can work my way through it mentally, but why not look at it visually? Go to hex FD. We have 1, 1, 1, 1, 0, 1. Zero, 1, which is 61. So we have a run of 61 of this color. And the next byte, oh, 61 plus 1. It should be 62. Then we get F, which is another run, but not as much. So F0, we mask off those 2 bits, we get C0, or not C0, 0C. No. C, oh, no, so it's 3, 0. There we go. So if we have 3, that's an additional 3, 4. So we get a run of 62 and a run of 4 for 2 runs there. Then we get, so I'm just trying to visualize what our output's going to be. So let's just do that. So we're going to get an RGBA with 255, 255, 255, 0. And we're going to run 62. And we're going to run, what did I say? 4. Then I should get an RGBA because of this byte, and it's 0, 0, 0. So red, green, blue, then alpha of 1B. Let's see here, hex. 1B is decimal 27. Then we get another RGBA. I said I'd run out the first 10 pixels, so this is actually not going to work out very well. That's all right. 0, 0, 0, 35. So what's hex 35 to decimals 53? This is the kind of stuff we would expect to see in our output. 35 RGBA because of the F, and then 00004E, 4E, 78. Uh, 78. You can see the alpha channels coming up over a couple of pixels. Not sure. Yeah, I just want to keep track of like opcodes then. QOI CPP. Okay. Oh, we're out of kernel already. That's always sad. So maybe we can't use pixel count or offset, but we can do an int opcode count equals 0 if opcode count is greater than or equal to 10. There we go. All right. Now when we run this, we should be getting the kinds of output I was just talking about. RGB, white, a run of 62 of white with no alpha channel, and then a run of 49. Did I do my math wrong before? 27, 53, 78. So those all look right. Each of these RGBA values is very painful, actually. I mean, how many opcodes does he have? Let me think about this. Could I do... 1, 2, 3, 4, 5, 6. Okay. So partly... these pixels look right here. Color. Do I have a thing that logs color? So ostensibly, this looks like we're getting about the right stuff. Just from that initial manual scan through. Which is encouraging, but those pixels are not being written to the bitmap output correctly. We have laid out our memory in RGBA. Let's see. So red, green, blue, alpha. Did he give examples of the hashing? Okay, so blah blah blah. I'm fine with most of this. This run appears to work, given the current color. This should be the should be able to output some of these colors. Hey, Dravest, doing good today, doing good. Trying to debug our QOI image decoder. I'm wondering if my bitmap output is wrong. But yeah, doing pretty good. How are you doing? You just about ready for Christmas? It's always so much preparation. How are the web pages going? Any good client projects you're working on? This had 2 runs in it. One was 62. All right. We're just trying to get some debug information to show us where we're at. Where are we going wrong? After that initial run there, it's looking like we are right. I changed that, so it should not be 6249. This one confuses me, but that may just be me. This output confuses me. Oh, opcode counter gets incremented. Oh. Run 49. So if we go back and look at our test card, magic number 256 by 256. 4 channels, therefore we have alpha channel. This is 0, so it's sRGB. We get F, which is 4 value pixel, F white with an alpha. FD is a run, and F0 is a run. Which means I mathed wrong. 3048 plus 1 is 49. Yeah. Scratch. This is indeed 49. Because F0, take the 2 bits off for the F, and you're left with F30, which is 3 times 16, which is 48, plus the 1, because there is an inherent bias in the system. Right, so let's change our threshold. Opcode count. Let's go 100 pixels in, or 100 opcodes in. This is far enough in to actually get some useful information. All right, so transparent, slowly fades into a black. Then it transitions to white. So if we're looking at the image, so this white line here between the opcode 10 and 11, that's happening right here. This pixel, transition from black to white. Now we should see another transition from white to black. Here. And that fades off to alpha until it gets to a run. Oh, we've seen this value before, so we can look it up. 123. It's this one. Okay, I guess I could believe we have that. Look up other indexes, find eventually we faded out, and there's a run. I'm not gonna lie. That's a lot of pure alpha in a row. So let's take a look at what's happening here. This is about the halfway mark. Then we had 62 plus 49. I would kind of expect about 62 plus 49 to happen here, and then about 62 plus 49 here. 62 plus 49 times 2 divided by 62. I would expect 3 62s, 1, 2, 3, and then the residual. Okay, so that actually tracks. Then we get a different values. Indexes, runs, run of 7. So basically this is row 2, and somewhere along here alpha hits full opacity and goes to here. Then we're going to go, so that's the black run of 7. Then we grab the color 38, which is white. That's this pixel right here. And run out 15 pixels over to here. 7 more black pixels. Then it does the little alpha fade thing. Fade out, fade out. We'll just fade it out. Then we run out a bunch. Honestly, all of this looks pretty reasonable. Oh, let's see here. Oh, C-Films. Howdy, howdy. How are you doing? We're doing good here. We're doing good. How's your web page going? You were doing some refactor, some cleanup, some readability work. Does it feel more readable yet? Honestly, these all look right. So, possibility 2. Possibility 2. There's something wrong with my bitmap writing functionality. Red, green, blue, alpha. Whoa. Okay. Who wrote this junk? Honestly, where did I get that? I mean, that's definitely not right. Okay, well, we're gonna take this thing, we're gonna cast it as a uint32t pointer. And we'll take the contents of that pointer and see what we get. Okay, now if we open our test file again, that we just outputted. Okay, at least we're getting colors now, so let's show what that looks like. Where is the thing? OBS, over here. Oh, I am showing the thing. Okay. So yeah, we have some colors. It still doesn't look like this. Okay, so maybe these all look correct to me. Or all of the ones I've tested against. Green, blue, alpha. It is, oops. It is possible that the order is not what I think it is. Okay. Okay, so if we show this latest image, the colors are different, but it's not more correct than what we've had before. So here's the black and white. That alt text is written essentially top to bottom, left to right. Hum. I think in the general case, but this data is not what I'm seeing. So if I go to here, take out the log pop for every one of these. Mm. Basically log the last color we wrote that opcode and the index it's at. Don't need to go to 100. Let's just go to 15. There's 0, 62 on 11. Then on 12 we get some colors. Does color can have an index most of the time? Actually, I would just do this. So we get our current, added at some index. In some pixel. Let's see. The strangest part. Okay, let's go down to here. There we go. Okay, so we're going to see if our hashes are correct, but honestly, I don't think that's the problem. Where did my hash go? Actually, why are we doing that? Having ideas about my own image format now. It'd actually be quite similar to QOI. I think there's a lot of really good ideas in here. But I wonder if I can make it even easier. I'm gonna go. There's not an index within the first 15 opcodes. It's fine. Current color, pixel 114. let's go up just a little bit longer before we, let's see here. Let's say 15. Let's go to 25. Okay, so index 14 should be 247. Nope. Interesting. Index 5 should be 255, 255, 2. Oh, interesting. So things aren't being put in the hash correctly. I think. Where do we do that? Then we have it there. Put it there. When we get an index, we don't have to. When we get a diff, we do. And so it does it there. So we just miss. Looks like we may have test. Maybe we weren't properly hashing recent values. So when we get index 48, there's a real value, and if we find $48, 255, 221. Okay, now let's try loading our image. Hey, no, that's not. That's not better? How is that not better? How is it not different? Tools bin, that doesn't help. Okay. Don't understand. Okay, so the image doesn't look any different. So did we actually make any changes that mattered? We kind of did, but did I just do the build wrong? Huh. So this is what I'm seeing now. Let's see if I can share the. Oh, you're looking at the image. Never mind. to bottom, left to right. Okay, so this is what we want it to look like. This is what it's currently looking like. Made some changes, but it didn't seem to fix anything. Very confusing. 8 byte end marker. Color space channel fields are purely informative. Images are encoded row by row, left to right, top to bottom. We start with red, green, blue, 0, alpha 255. An image is complete when all pixels specified by width times height have been covered. Pixels are encoded as a run of the previous pixel, an index into an array of previously seen pixels, a difference to the previous pixel value in RGB, or full values. The color channels are assumed to be not pre-multiplied with the alpha channel, a running 64 element array 0 initialized, of previously seen pixel values is maintained by the encoder and decoder. In the encoder, if the pixel value at the index matches the current pixel, this index position is written in the stream as index. Yep. Hum. Just reading through the spec again. It doesn't take long, but hmm. Printing out the values makes sense. I see the opcodes happening. I should be dumping that pixel data just fine. Okay, so let's go look at our code. Let's go look at where we can go wrong here. So often what happens when I'm stuck in one of these positions is I'm making assumptions that are wrong, or I'm looking in the wrong place. Probability number one, this is working correctly in as much as I should get some pixels correct in the output, like it just should. So see that the value is being set to what our current color is. Therefore, maybe the problem isn't here. Maybe it's in here. Get our texture. A bunch of uint 32s instead of bytes. In this case, it's just texture subscript index, write out that value, which tells me it's really just this, which could explain a lot of our strangeness. Actually, run it. Close the old one, open the new one with GIMP. Oh, that's closer. Okay, so let me share that screen. Bingo. Okay. Now, this is a lot closer than this, and it looks to me like I'm just upside down. I flip left to right, and I'm flip left to right. So if I write my whole array backwards, oh, I know why I'm doing that too. So because of where I copied this code from, that's QOI. Let's see, because of the way we write this thing, just write everything out backwards. Let's close that. So let's, too many context switches. Here we go. So all I did was instead of going from 0 to text with text height, we're going from text with text height down to 0. We're just putting everything in backwards. We'll try that. Run it. Then reopen my bitmap. No, not that one. Open with GIMP. There we go. And then we compare. Still slightly confused. Let me share this one. Okay, so if you see, here's our desired output, and here is our actual output. It is flipped X, Y, but not vertically anymore. It is only flipped horizontally. But as far as the fundamentals go, this is not bad. We'll have to run some other tests, obviously, to make sure we have good coverage of all the things, but QOI is pretty much working. I have some thoughts. I should propose a QOI 2. But that's not important. We're not going to do that right now. Maybe I should write some notes, though. Because it is a very nice format, I think. QOI alternative double opcodes. Double 4-bit opcodes. Little 16 ops. Some alternatives. Color code. White, black, alpha. Yeah, so much of this is actually really good. I really like the QOI format. I think we can do something slightly better. But anyways, so we are flipped. We don't care about how long it takes us. How is the project going? Well, we are working on image compression. Right now we're storing raw data, and it's about 64 megabytes within our executable, within our code. And we're trying to shrink that using QOI format. The top of the chat, the pinned chat, is a link to the entire QOI format. It's a one-page document. So we've just about got it debugged. We have a horizontal flip issue where this is the test image we want to look like, and here's the output of us reading in that test image and dumping it out as a bitmap. So we just have that horizontal flip, which is not that bad. And yeah, that's kind of where we're at. We want to embed QOI encoded data instead of RGB raw data. and see how much that compresses our project size. We've got the audio compressed, that's about 25%. So yeah, overall looking pretty good. How's your webpage going? I haven't looked at it in a couple of days. Yeah, it's flipped horizontally. All right, so what if we do the following? Let's go back to the code. Or int row equals 0 row less than texture height plus row. Int column equals 0 column less than texture width plus column. We do this, which is basically row times texture width plus column. So yeah, overall pretty good shape. I think we know enough about QOI to do the encoder as well, mostly. And yeah, we're looking pretty good. Okay, so let me open that file. So this should be upside down and backwards. Oh, it's just upside down. Which actually is normal because of OpenGL, we interpret all of our images upside down. So this actually may be correct. So let me show. Here it is. So this is desired image, and the red, blue gradient goes red to black, left to right. Here, it's just upside down. So I think we just need to go through the columns backwards and or the rows backwards and we're fine. So let's go do that. Because OpenGL, the Y is inverted basically, so all of our texture handling is upside down. CFilm's website project is going well. Good, good. I know you did a bit of a cleanup, code readability. Feeling better about your code quality? Not follow. We want to go through the rows backwards. Texture height, while row is greater than or equal to 0 minus minus. Okay, I think we've won the whole shooting match. Let's share the image. Okay. Target image. This is what we want it to look like. This is what it actually looks like. I think we've got it. Excellent. So we should test some other files just to be sure. Oh. I'm not sure we do have it. Hold on. What's this other image? Uh-oh. We have some garbage values down here. What's going on with those? Uh-oh. Were those there when we didn't flip? In fact, that whole last row is messed up. There's no white-black transition here. Curious. Okay, well, let's go debug that last row then. If we go to not this one, this one. If we go through our rows forwards, row is less than texture height. Nope, I know what's wrong. -1. Can't start out texture height. We're gonna get garbage. Run it. I also would expect like a seg fault, but it doesn't do that sometimes, so. Okay. Now that last row looks correct. Let's get back on the 8th screen. So there's that. Nice. There we go. We have just used an alternate encoding mechanism, and it works. So our bitmap raw is 257 kilobytes. The input QOI image is 24 kilobytes. So excellent compression on that image. Let's do Wikipedia test. Let's do a different test. So let me show you the desired image. Open with GIMP. This is what we're going to shoot for. Let's add that to our tests just to see. I need my code quality has improved. Very good. Hide GIMP. Test this one. Because we can. Meanwhile, in QOI, -d debug QOI. Those are an option we're going to want eventually. We're going to use that to hide some of the rather silly things we do. Pound in if def. Okay, so this trace code count I think only exists within debug statements, therefore you can come up here with the trace. There we go. Test QOI. I won't even run it. Error, invalid file format. That's unfortunate. Oh, we gave it the PNG. What are we doing? We give it the QOI, we output the BMP. That's our bad. Oops, it detected the wrong file format. That's always happy. Assertion failed. It loaded completely wrong. In this case, his QOI image is actually bigger. Oh, it is, yeah, it's not much bigger. Okay, so X mode QOI. Okay, let's see here. X 480. No, it's not right. It's oh 0840 1 2 3. I'm told 1152. Oops. 1152. 1152 in hex is 480. Which is 0 1 480. Okay, I agree with that. And then I'm told 858 is 35A. So this is width and height. These look correct. 3 channel. There's no alpha. 0 0. So it's sRGB. FE red, green, blue. I don't know. Okay, so we kind of know what this file needs to look like. So when we read this file, it's reading something wrong, and the assertion is failing because the size is wrong. So it's trying to load this thing, and it's getting some weird numbers for its size. I'm not sure why this one would be correct sized and this one wouldn't. I need to go. Hope the yerba think it's this spelled this way is good. Yep, it is good. Thank you. I'll see you tomorrow. Have a good one, Drevest. Okay, so we're clearly not getting something, although assertion failed. Line 113. That's when we start the decode. Totally agree. That should not be that way. But this read, this is kind of odd. We scan in width and height here before and after any of this. Swap Let's do something else. That's going to be width and height. And the contents of width and the contents of height. These are used for different purposes, so let's take a look. Okay, so let's get some weird numbers. Byte swaps them. These are some odd values to have here, especially after a byte swap. Huh. One loads correctly, one does not. What have I done wrong? I'm so close, and it actually is not that far off. Endianness swap. Width and height. All right. Short restroom break. Then we'll figure this out. Be right back. Right, so the question is, what have I done wrong? 0x modulus 0, 8x. 0x modulus 0, 8x. Kind of the same thing here. Except we're chopping it off there. Okay, looks like I have a problem in my endianness swap. Right there. This byte is not actually being moved. Oh, because of OR equals? Let's see here. Endianness swap. Let's go take a look at that. I'll bet that's the problem. Okay, let's see here. H2NL and N2HL. Oh, yeah, I don't want those, I think. Host. That's what H2NL is basically host to network layer and network to host, or long. I guess it's host to network long and network to host long. For a long time, there was a big difference between network endianness and your machine's CPU endianness, and the two were just different. So you had host to network and network to host swaps, and if your machine matched the network endianness, these were no ops. So your machine is probably big endian, and your network was little endian, if I remember the convention right. It's been a long time since I looked at any of this. So, and these are for long values. There's also H2 host to network short for 2 byte values. I mean, this looks an awful lot like what I was doing. So that's awkward. Okay, so what I've got is this value bit shifted 24. So it basically takes a 32-bit value, takes that top byte, marches it all the way down the bottom. That's fine. This one seems to work fine. This one seems to work fine. So why is this one not fine? Value and FF. So it grabs the lowest byte, masks off everything else, and slides it 24 bits that way. Maybe, I mean, we don't even need this, do we? Oh, and now it works. That mask was killing me. It loaded. That's the size I expect. And now I should have a test output bitmap image, which we will open with GIMP. Maybe I've screwed up something. but I don't think I have. So if we go to OBS, show the GIMP, this is the target file, and this is the output we generated. So here's the PNG that came with the example pack, and here is ours. So I think we're done. I think we've got it. I think we've got QOI encoding or decoding in the bag, which means we can test. Ugh. All right. We got to go the other way now. We also need to be able to encode, not just decode. So that is step number 2. We've got this one done. Very nice. Now, oh, good heavens. We can run those tests, that's fine. Now we want to take any old image and dump it to QOI. So we're going to do that. Wikipedia 08 and Wikipedia 08 PNG to QOI. So we get a PNG file and we read it. We probably should rename that actually. Write bitmap, read PNG. That will probably clarify things a bit. Okay, so we read our PNG, blah, 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 file size into our image. PNG loaded something by something. Modulus the bytes. So we need image width, width, height, and label. Width, height, file size, and image label. So that'll make it look more like the other one. Wrote so we read our image, we clear our image, we write something. And actually it's to QOI. Okay, all right. So we need to encode a payload. QOI encode our image data, image width, image height, and then we need a QOI, let's see here, size. So QOI encode, then we write. This probably should be like QOI payload or something. Okay. That looks about like the code we want. Think. So reading a PNG, encode it to QOI, then dump it to a file. And then we can look and see how we did. Now, I don't think we've implemented any of those functions, so write and encode are not done at all. So if we write, oh goodness gracious me, informational only. Payload size in header. No footer. 6 bytes. CRC. Could be more, be better. Footer. Think. Footer. CRC would be better than 0x1, 3, 4. 1, 2, 3, 4. So that's already a 16, it's an 8 byte. 2, 3, 4, 5, 6, 7, 8. 8 byte. For 4 more bytes having a CRC 16, I think would be more valuable. Set channel RGBA plus 1 byte. Delta channel. I'm not even sure that would be needed. Not really. Although, if if we have two delta channels, you could even have basically this would add 4 opcodes, 4 more opcodes on top of the, and then this would be 1 more opcode. That would add 9 opcodes, which would probably increase your compression without making things more complicated, really. I'm not even sure I really like the Luma, but I'm not going to argue with Luma. The guy who invented this is clearly much smarter than I am. If we never use the Luma, I'm not too worried about it. For 8, it means if we wanted 2 delta channels, that would be 2 bytes. Which I think is more efficient than delta channel, than set channel, set channel. That would be 3 bytes. This would get us, anyway, that's besides the point. Okay, we're looking at, I just set up VS Code to trim trailing white space when the file is saved. Yeah, that's how I've got my Emacs set up too. As soon as I hit save, it cleans up trailing white spaces. Okay, so when we write out QOI, the first thing we're gonna do is open a file. As write mode binary. Yeah, there are certain types of tasks that are just better suited to have your IDE development environment take care of it. And other than being exceedingly slow, VS Code is not as bad as some. Write, read. Decode, here we are. We are going to assert these things to be true. Width, height, and size. Okay, that's right. To our output file. There it is. Oh, that's right. This one's backwards. Pointer to data. Size of entry, count of entries. Ugh. That kind of argues for not being undefined, but a static const unit 32t. That's fine. So now we can put magic number, the address of the magic number, size of magic number, and the count of magic number. Okay, looking at the spec. Here we are. Then we need 32 bits of width. And height. Already I can see a pattern emerging that's enough. We will always write out the same value. We need a uint 8t for, what is it called? Channels. We'll always output 4. And what do you call that? Colored space equals 0 for sRGB. Or linear. Okay, so channels, you know what, let's just do it. Right, a value. Write the address of the value, the size of the value, 1 out file. Right, colored space, okay. That's basically it, and then we write out the QOI payload, which will be QOI size of character size into out file. Right, 0. Seven times. Then we can write a 1. close our output file. Done. Okay, so that's part one. Not really that hard. This is the tricky part. And maybe we just pause here. Journal decoding. QOI decoding is working. Most of the issues were how we were packaging it up. The output into BLP. Decoding seems to be working. Okay. Decode, encode. Assert that raw is unable to roll. Here's one of my problems. And it doesn't really affect our program. When we encode raw image data, we don't know what the output size will be. So we could use a vector or some kind of growing container. I think the fastest thing to be, wasteful though it is, would be to choose a size that we think we can fit everything into, which would be, well, width times height, right? I'm thinking pathological thoughts here. I kind of wish I had a bucket array structure I could access reasonably. So how to estimate a reasonable output size? One way to do it is to encode once without baking. Well, without actually writing it to anything and just keeping track of the offset, which would give us our size at the end. I can think of very simple pathological conditions where our output would be larger than our input raw. That's always discouraging. Hmm. Do a linked list of fixed size arrays. Then gather it all together at the end. Hmm. Okay. I need a pixel count. These both have to happen. I'm glad I found that feature. Yep. Yeah, any kind of, if you're going to have code standards for style, it's best to just have that as part of your development environment and not part of your build or your commit environment. I think it's just happen automatically. Although you can't be sure anybody else is going to set up their system correctly, so you still kind of want it on your revision control to check, auto check, and reject code style violations. Those are the easiest things to fix. There's no reason to ever have them checked in wrong. So encoding for each. Row for each column. This is our raw data. I think it's just red, green, blue, right? It's red, green, blue, alpha. Good to know. So my color is laid out backwards of integer memory. I now have about 45% of my code files matching between GitHub and website hosting. Nice. Yeah. That's good. It's good to be consistent. I actually have a couple of Git things I need to tidy up myself. Every time I generate one of these warehouse files, it blows up. Not in a good way. Row times height plus column. That's our pixel index. Yeah, I can think of a simple between 1 and 4 pixel example that would be trivial to make, where the length is bigger than the input. Oh, we also need a 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 plus 2, 3, 4, 5, 6 is 16. Okay. I don't plan on supporting Luma. We'll use everything else though. So we need to get the color out of our raw buffer. Equals the contents of passing this to a color pointer of our raw data. Plus our index. Should give me the upper right-hand most corner. Let's just get something working here, right? Okay. Dash D debug QOI. That's fine, that's fine. Pointer. Yes, I know. We'll get around to it. its position. Okay. So we're going to read in test card RGBA. And that first color is white, white, white 0. And over here, this blue one. Let me just check. That is 29, 52, 99. 29, 52, 99. Okay. So we are indeed getting the upper right-hand corner, upper left-hand corner of the image. And we are getting that color correctly. Perfect. Let's get 2 and then 2 pixels out of here. I'll check both values. Oh, that's not right. Okay, that's awkward. This one also looks wrong. It's like it did a rotation. Oh. I think I know what's going on. Raw. Ready? We're going to do this. Color star pixels equals we're just going to reconsider raw this way. Okay, that's looking better. Correct. This one, 32, 53, 98. I'm just going to sample that one real quick. Make sure it's 32, 53, 98. So, looking good. All right. So we get our color. I want to compare it to the current color. And there's sort of an operator precedence here. We want to choose the operator that gives us the best compression. So first thing we want to do is say if C equals current repeat one thing I want to do, a couple things I want to do. Oof. I want to get the next most efficient one is probably the index lookup. If array at hash of C equals C. So if we look up the hash and if that is there, that's an index. look up, which is not too bad. So there's two of our ops. I need to look at the rest of the diff. I don't think I'm going to bother outputting Luma. If we have run index diff RGBA, then we should be fine. So we just need a little helper function int is close or are close. Color A, color B. Equals A dot red minus B dot red. Green, blue. Alpha is not touched. Delta red, delta green, delta blue. If okay, we have an array, we have a current color. This is another one of those cascade things, I'm afraid. A dot alpha, A dot B, and we need to check 4 things. -2 less than or equal to delta red, and delta red less than or equal to 1. Green and blue. If these two are close. We're doing A minus B, so we want to know if C and current, and maybe we're backwards. Maybe curve then C question mark. Come back around to this. Basically, we're looking at each pixel and saying, what's the most efficient way to re-encode this? Repeat is amazing. Index is pretty amazing. If two colors are close, then we do the diff A minus B. So cur is actually previous, if you want to think of it that way. In fact, why don't we just call it previous? And color C is current color. Current minus previous tells me how much to add to the previous thing to get the current. So that, I think, is correct. Okay. Else if current dot A equals previous dot A. So we haven't gone with anything else, then RGB. Otherwise, and this is like the worst case, because here RGBA is 5 bytes to represent a color. So this is bigger than the input data. We're going to skip lumens for now. Skipping Luma. I don't really want to think about. Let's see. Maybe we call it called CanDiff. Maybe we need a can Luma bool. Can Luma color A, color B. Return false for now. Implement. Okay. I think that's basically it. Where repeat or run is a little bit interesting. So index is the easiest one. We hash the current thing. And we write it out with the opcode, which is index 0, 0. Actually, it's just a hash. That's it. Diff needs these three. Then we add our bias of 2. Instead of A dot, we go with current, current dot. Instead of d dot, we go with prev dot. Because when we get into our code, we're going to take our previous thing -2 and add that to, or take a previous thing -2 delta. Okay, well, maybe we're backwards. It'll be fine. We'll figure it out. But diff is diff 0, 1, which is what? 4. BR bit shifted 4, DG bit shifted 2, DB. That's basically that. Can Luma. Luma was 1, 0, so that's 0x80, or stuff. This one. We actually write out FE. Then RGB. This one we write out FF RGBA. I think that's the structure of the code. But we need a run count. Int run count equals 0. And actually that kind of breaks up all of this. If run count is not equal to 0, we're going to have to reset run count to 0, and we're going to first write out run. Run is 1, 1, so that is 12, which is A, B, C, 0x C0, or run count. If run count is greater than 62, if it's equal to 62, and we still do this and this. So we can only count 62 minus 1. Minus 1. That's basically it. So as long as they're equal, we keep incrementing our run count until we hit 62. Then we dump the result and keep going. If our run count is, if current is not equal to previous, we dump out the current run count, if there is one, before we proceed. So a little bit of duplication here, but I'm not too worried about that. Okay. We're skipping Luma. Okay. Anything else we need? how many times Luma shows up in some of these images. Right. In this case, we're writing out a byte. Most of the time, we're just writing out bytes. So maybe we go uint8t b c0, or, I mean, it's basically this, right? Run count, that's 1. Then we okay, so that's 1. Oh, no. We get our byte. Get our byte. Current.r RGB. A. So we got the bytes we need to write out, except for the Luma one. So up here, can we Luma? The question is kind of similar to this. Luma, if green diff fits in 5, it's between -32 and 31. Green is the key component here. Green -32 and DG less than equal to 31. DR minus DG and DB minus DG. DG minus DR. Other way around. DR minus DG. DB minus DG. Return. This has to be true. Between -8 and 7. Oops. Of D R minus DG. And blue. Oh, the wrapping. shoot. The wrapping made sense the other way. I'm not sure I'm clear this way. Wrapping. And wrapping. Okay, we're just going to ignore wrapping for now. If we can, Luma, blah, blah, blah. BG. So there's a negative 32 bias. DR minus DG plus 8. Or DBDG plus 8. Bit shifted 4 bits. Actually, a lot of the wrapping would go away with my. Let me further simplify things. Okay. I do kind of want to write my own now. This Luma has that built in. Yeah, 8 and 32. Okay, okay. So I think this is correct. Okay, so instead of capturing the byte for each of these, we dump out the bytes to something. And again, I know how to pathologically craft it so that we always end up with a larger file than our input data would suggest, which is one of the reasons for some of the other features I want to add to a comparable image format. But I kind of want to stick with QOI because at least then I have examples to run against that are not my own. Or do we just ditch QOI and do our own image format. Largely based on QOI. So many options. I'm out of hot water. I'm out of hot water. Do I make my own image format? If I do, is it possible for me to compress things smaller than QOI or not? And honestly, right now the implementation would probably be comparable in speed. If not better. I mean, maybe it would be worse. I'm not claiming I have any genius ideas here. I don't want to do this. Now that I've seen QOI, I kind of know what he's doing to do the compressions. And this, I think we could get more. I think we can make better compressions. Anyway, I'm gonna pause for a brief. I'm gonna get some hot water here. Do I want to ditch QOI at this point to make my own? I mean, I kind of want to finish implementing QOI anyways. Do I write my own image format? Heating water for yerba mate. I have to think about this. All right, so I'll be right back, and we'll probably finish QOI. There's no reason not to. I'll be back. Okay, we're back. More water, ready to go. We just need to finish QOI. Let's not get too distracted. And now I'm gonna do the stupidest thing. Like, there's no way this should be the right way to do it, but we're doing it. Width times height times 4. We're going to be allocating as much memory as our original image. And then putting a byte will do the following. It's the bottom of the bottom of this one. Previous equals current. And our array of the hash of the current equals current. Shoot. I have a mismatched parentheses somewhere. Row, column. That's the function. I think that fixes all of our notation issues. Okay. Put a byte into result sub contents of size plus plus equals B. Is that it? No, no, what is it doing? Search for, let's see here, F3. Search for okay. Search for B equals Oops, not that one. Okay. Current equals previous. All right. Hash equal. RG B and A. Equals. A for A dot for current dot. B dot for previous dot. Okay. Result. Expansion okay, where's my result? Result. Yes, it's terrible abuse, but it's fine. Unused variable pixel count. Unused variable QOI payload. So in theory, let's see, where's the thing? That is not 18 kilobytes. This other one is over 2 megabytes, almost 3 megabytes. What is this rote? Rote label? Okay, I doubt this is going to work out terribly well, but oh, rote 0, 0. Why are we doing this as modulus D? I do not know. Modulus S. Good heavens, that's terrible. There we go. Like I said, I may not be doing everything quite right, but when we have 3, 4 megabytes, we should get a lot more of that. But anyways, this did indeed output some files. .32 on the RGBA. So I'm not getting near as much compression as he is. I'm not even sure I'm doing it right. So question number 1. I'm going to read these in and out as something else. So instead of this, I'm going to take the output of the previous thing as our inputs, and we're just going to call these X, as in very unlikely to actually work. So we're going to read in a PNG, we're going to write out a QOI, we're going to read in the QOI and try to dump out a bitmap. That's the plan. I'm not sure that succeeded at all. Yeah, we're stack dumping somewhere. We'll see where it crashes. So we have to end in a swap when we dump it out. That's one issue. That would definitely cause it to crash if I was getting the wrong file size. Assertion failed. Oh. $65,536, $65,487. Okay. So that is indeed a failure. What if we go to can we Luma? Return false. Let's just not do that. Doesn't seem to have helped. Our computed size is not equal to our actual output size. Oh, I'll bet I know why. What's the difference between these numbers, do you know? It's 49. That's the length of our last run of alpha. So an alpha has to be trimmed up at the end. Or not trimmed up, but it has to be terminated at the end. So in encode, you do this at the end of the loop. Okay, it wrote out the files. Now we can compare the full round trip, I think. Well, not great. We have some issues. Okay, so let's hop over here, but not as far off as I thought we would be. Okay, so here is the original PNG. When we take this and we shove it into QOI ourselves and we read it back out, this is what we get. So we have some issues. It's true, but not that bad. There we go. Oops, not that one. This one. So this is the original desired. This is if we go full round trip. Not far off. This one, however, oddly, is way off. We aren't even close. Yeah, not even close. So that's too bad. Our compression ratios aren't very good either. So we still have some work to do. But not bad. I imagine let's just look at our code. Can we not infer put that back here. Exit count times 4 bytes. Okay. So encode if blah blah blah. We do the runs. Fine. Put the run. That's fine. Index. We put the hash essentially. I wonder. Kind of want a histogram of how many times each opcode is used when we read a QOI. Is this saving a ton of space? I don't know. It might be the diff or the wrapping. So let's go down here to debug QOI. Let's make that a nice small number. Max op codes to log. Okay. Int histogram. There are 7 opcodes. Histogram equals 0. Okay. So what we're curious about is from some of these real images, how much do we actually use these different opcodes? Histogram 1, histogram 2, histogram 3, histogram 4, 5. So I'd expect one more. There's only 6 opcodes. Oh, I'm remembering 1, 2, 3, 4, 5, 6. Yeah, there's only 6. Then at the end, nope, this. That's not what I typed at all. Okay, lastly, opcode, histogram. I'm not looking for anything super generic here, so we just go with 0 is RGBA, 1 is RGB, RGBA, B, then we got index, diff, Luma, index, diff, Luma, run. Histogram 0. Okay, we want a percentage, so 100 times histogram sub 0 all over opcode count. Two, three, four, five. We're gonna do this. Critical error detected. That's unfortunate, but I kind of don't care. So when we read in test card RGBA, there are a lot of runs. There are some Luma and diff, okay. Then when we load in really. Zero RGBA. I guess that makes sense actually. Mostly indexes, not very many runs. Some diffs and some lumas. Okay. Not near as many diffs or lumas as I would expect. But I'm also not checking for wrapping properly, so that could be why diff is not working very well. Let's see. Not sure. I must have hit a keyboard shortcut to change the scene there. Okay. This is for what we can do is change our max opcodes to log to 0. Okay, so we got our test card RGB, our test card RGB. These things are not even close to the same. This one compares with this one. Yeah, our diff sucks. I don't know how it's getting a Luma at all. It shouldn't. I thought we shorted that out. If we go to, can we Luma? We just say no, you can't. So it should never get in here, which is a little bit odd. All right, if equal is equal to the previous increment around count. If we're high, keep going. Otherwise, we see if we need to break up our run. Okay, so diff. So the wrapping, we need to modulus 256 somewhere. The question is where? And the short answer is this thing right here, I think. So if we have 0 or 1 to 255 modulus 256, I think that is what needs to happen for the wrapping to work more consistently. We don't add 2 here. Let's see here. 255 to 1 would be 1, right? So 255 minus 1. What's the modulus go to correctly do this? 255 minus 1 would put me at 254. We need wrappings. What if our current is 1 minus 255? That would be negative 254. We take the modulus, that would be 2. Which going from 1 to 254 is correct. So this happens fine for the current number being very, very small and the previous number being very, very large. But the other way around, 255 and 1 puts me at 254. PR is greater than, let's see, something we can add 1 to. Yeah, this wrapping thing is kind of killing me here. Hey, JTL, been a while. How's it going? It's going good. It's going good. We're doing some image compression work today. We're going through the QOI image format, which is very clever. But now that I've seen it, I think I can do better. But I would like to get QOI working first. So we're trying to debug what I'm doing wrong. There is a very simple implementation I could just copy paste, but I don't want to. I want to do it. I want to understand it. So that's where we're at. Debugging our code. How are you doing today, JTL? So if it's 255 and 0, 255 and 1, doing good. First minute I've had to sit down and over a week, nonstop shoveling of dirt and mud. Oh, fun. Oh, fun. Yeah, it's been rainy too, so you've really been having to slog, haven't you? Worked from sun up to about 11 o'clock last night trying to get ready for the foundation pour. Is that foundation pour today? Probably not, since you're watching stream. Interesting. Well, hopefully you're ready for the foundation pour. You should have called me. I would have come help you shovel. So the cases of wrapping. Integer wrap distance difference. Hmm. Are you incorporating compression as part of Word Sleuth? Yes. Foundation pour tomorrow, but had to prep the area to do forms today. Oh, goody. Oh, it's been a while since I've formed up a concrete slab. And I never did real foundations. I only did pours for grain silos and irrigation pipeline junctions. The building requirements were not nearly as strict. Yep, we're trying to get our image data compressed. We're using 64 megabytes of image data. We would like to use a lot less. And we're going to use an off-kilter image format to do that. I'm not finding what I need here. Yeah, we've already got the audio data compressed. We're down to about 25% of our original audio file size. So that's nice. Wrapping. All right, so I have to think this through. We get the change in red. And that's fine if it's like, you know, the current value is 18, the previous value was like 16, right? Well, or if we're going from 16 minus 15 equals 1. In other words, if we get 15 here and we want to go to 16, we have to add 1 here. If we swap it, then we need a minus 1. So that all works fine. But the question becomes, what happens when we have 255 minus 0 or 0 minus 255? That's the goal. Cool, I've never looked at compression algorithms before. Well, the easiest thing with audio was, let's just take a look at it real quick. To say all of them are mono, like I measured the variance between the left and right channel and then divided by the number of samples, and it's tiny. It's almost, the number of files we have that actually use the stereo is 0, effectively. So we're just taking a mono channel, taking the left channel, dumping it straight in, and so that halved our data size. Then we did do MULA encoding for most of the sounds. Some of them sounded bad, so we put those ones back to PCM. But we can now, per sound file, choose mono, stereo, MULA encoding, or PCM, and those combinations will all work. So we just pick the size that roughly gets our compression down to 25.38% of the original size of all of our sound data. So that's the simplest. But image data, it's a little bit interesting. And what we're looking at is this. Let's see. The decoder works. So decode. What you do is you have a current color, and then you have an array of colors you saw recently. That's the starting point. Then you go through all of your data in the QOI file, and you say if the byte I just read is FF, then that means that the next 4 bytes are red, green, blue, alpha. If the byte you just read is FE, then the next 3 bytes are red, green, blue, no alpha. Otherwise, we just look at the top 2 bits. And if the bits are 0, 0, then it's an index into the recently seen colors. If the 2 bits are 1, 0, then it means it's a small difference between the colors. And the amount of red, green, and blue we have to change it by goes here. So we just update our current color and dump that in. So that's a bit of a save, right? If your colors are very close, but just slightly off, this works great. Then we have Luma. I think this has to do with the luminosity of a pixel. So basically the brightness is largely driven by the green color. So as you move on a solid color into the shadows, your luma is coming down, and that proportion is roughly represented by this equation. So it's saying we're staying in the same color, but we're changing our brightness. And that, oh wow. I think we have a typo. Anyway, not a huge deal. And this one is really the big savings. If you have a whole bunch of the same pixels in a row, just keep outputting the same pixel over and over again. So for 1 byte, you can write out as many as 62 pixels of the same color. And when you do that, you get similar compression to PNG, but the encoding and decoding is much, much faster. PNG is a little bit more aggressive, a little bit better for actual total compression, but it's actually a very complicated file format. PNG has multiple compressions that it can use, and it looks at all of your data before it decides which one to use. So encoding time is a bit of a nightmare. This QOI image for file format, it's just pretty good for images all around. Very clever little file format. Now, I think we could make improvements to this file format. Make something close to, but not quite it, but I probably should get QOI working first. So our decoder works great. It works fine. It's the encoder we're working on right now. Just trying to get it so we can go full loop. We can open a PNG, dump it out as QOI, read in the QOI, and dump it out as bitmap, and make sure that the pixels look about the same. So that's where we're at. And we have this question of wrapping here. Basically, this says if the 2 reds are close, so delta red, delta green, delta blue, if the deltas are very, very small, and if the, B.alpha, if the alpha channels are the same, then we're good. So that's one problem we had. Oops, we were comparing alpha to somebody else's blue channel. But then we have this concept of wrapping. The difference between 255 and 0 should be 1, because it takes 1 bit to roll over that 8-bit integer. So that's what we're looking into. Run Python. What is 255 modulus 256? I thought as much. Minus 255 is the correct thing. So when we get this case, we can modulus 256, which is right, which is what we kind of had. So we just add 1. This one we need to subtract 1. And basically if our difference, if delta red is less than 0, so in this case we want to go from 255 to 0, we add 1. dr equals dr modulus 256. If the change in red is greater than 254. So in this case, we want to go from 255 to 0. We need a -1. This should also work for, so here's the 3 cases we need to worry about. Well, there are 6 cases we need to worry about. To go from 255 to 0 should be a -1. 254 to 1 should be -2. 254 to 0 minus 2 or plus 2. 254. Can't have that, can we? So if our difference is 255, our change in red has to be 1. Okay, the other conditions are 0 to 255, 0 to 254. We have to subtract 1, subtract 2, 1, going to 255 is equal to -2. So we can start at 1, subtract to 0, subtract 1 more to 255. The delta can always be 0. So that's it, I think. I don't like this. D, G, 1, 2, 3, 4, and then G to blue. 2, 3, 4, 5. Then we make sure it's between -2 and 1. I think that might implement wrapping. Sorry to run so soon. No worries. No worries. Gotta take rented equipment back to. Yep, I'll have to go back and watch this one though. Have a good night. You too. You have a wonderful evening. See you later. If we can diff, we do this. dr plus equals 2. G plus equals 2. D plus equals 2. Then we can put it. All right, let's try that. Oh. Previous to b dot 1, 2, 3. Permission denied. There we go. So I kind of expected this and this to be similar. RGB. Index 32, 33. Okay, that's closer. Diff, nope. Luma. How does it have any Lumas at all? Run. 28-ish, okay. Oh. My files should have no Luma. Because I'm not really implementing it right now. Shoot. Leave out. Actually, let's do this. Let's simplify the test. Let's just do the Wikipedia one. So we're looking at less stuff. Exited normally, okay. 0 RGB 6.9 as opposed to the one I outputted, which is 65%. That's really bad. We indexed reasonably. Our diff sucks. Our Luma I knew would be 0, so that's fine. So we are not catching diff like we should. If we used up a lot more diff. Interesting, interesting. Our index is going to catch. Why are we not catching indexes often? Neat. 31. We're actually catching index more often because there's a couple reasons it might be, but until we have diff and Luma. Run. We got more runs. Okay. Well, out of curiosity. Yeah, still crap. Still crap. Okay, the image looks the same, so no point in bringing that up. Okay, I'm gonna take a quick restroom break. Be right back. Okay. So let's do this. Ready? I'm going to take out the only complicated ones there are. If candiff, we're going to just say return false. Everything else should probably work fine, question mark. Okay, lots of RGBs, that makes sense since we don't have the other two sets of tools. We need to get a good use of index and runs. It's a little odd that we have more runs than that one. I think that's a little odd. But it still doesn't look right. In fact, it doesn't look any different. Okay. Our current and our previous colors are equal. Increment the run count. We fill up the run count, put the run count in, and reset. If they aren't equal, and we have a run, put it in and reset the counter. If the current hashed value is the current, then we put the hash in. We skip candiff and canluma. We dump RGB. Honestly, I'm a little confused. About why this doesn't look better. Oh. No. No, still just one byte. Value at the current hash equals the current thing. Shove put in. Oops. Could not make that simplification. Actually, are they not equal? Then we have to do 0xff. Let's do 0xfe. So if our alphas aren't equal, we use this. It should make a difference in this case. Should just run. Open with give. Take a look at our new file. It is still a disastrous mess. Why? Why is it so hard to encode this thing? Oops. We may not have been testing what I thought we were testing. There we go. Now maybe the image will look different when we load it. Nope. It's still garbage. 429. Yep. Huh. Load. This is the original test QOI file. Don't have this bitmap. We read the PNG in and dump out a different one whose size is bigger than this one. That's unfortunate. Hum hum hum. For pixel index equals 0. Pixel index less than pixel count plus pixel index, I guess. So this is very interesting. Oh, now we're getting the image out. And our compression is going to be not very good. So let me show, we've finally got our two images to be close. So this is what we read in original as PNG. We dump that out as QOI, and then read that in and dump it out as PNG. So that's what we get. Our compression is atrocious, which you can kind of tell from this. Most of our pixels are put out with the RGB command. And our run finally matches. Oh, thank goodness. I would not expect anything less. Run is like the best bit compression for information. So that's one you want to try first. You want that as high as you can. Let's get diff. Let's go do diff. Let's simplify this back down. $256. We'll just do the simplest things we can. I mean, actually, this is not the simplest thing we can. This is the simplest thing we can. It won't catch any wrapping, but it will give us a thing. Can diff. Okay, that's the simplest thing. It won't catch all of them, but it'll catch some. Which you can't see because oh, you can't see. Okay, all right. Run it. Now we have a bunch of diffs. 27.75. Oh, we've got the same amount as the original file. Cool. We have no Luma. Our index looks good. So basically, the difference between 6.92 and this should be this thing. And if the image looks okay still, that's the other question. Okay, the image still looks good. they look identical. So in this can diff, I just want to put that modulus 256 in here. Actually, you know what? Let's not screw with it. Can we Luma? We're going to ignore wrapping. That's not what I wanted. Ignoring wrapping. It just means that a few more will fall through to RGB than we might want. If we don't do the wrapping, blah, blah, blah. Okay. And Luma, blah, blah, blah. Okay, now we still don't have any Luma. I thought we built that. Oh, we don't have any Luma samples in the one we outputted. This one has almost 33% of its stuff that way. So the question is, why? Oh, I might know why. Maybe. Maybe not. DRDGDB, DRDG, DBDG. We can Luma if our, we did the same thing. B.alpha has to be equal. The alpha channels have to be equal for this to work. We had written instead A color alpha has to equal A color blue. There we go. Now we have some Luma. 33510. Oh, looks like we might have it. So our QOI image is now 14 kilobytes or so, which, of course, what's it doing here? Oh, why is the browser on? I did not turn the browser on. Very strange. Anyway. Comparing is the one I outputted with the one they outputted. They get a little bit more compression out of it. No, they don't. 1486, and I get 1486. Nice. So with no wrapping, I'm actually getting okay for that one. Okay, so let's try the other one. Test quad. We're gonna go back to test card. I wonder if this would be easier. I just did the round trip that way. There we go. So I'm going to get test by reading in a QOI image, dumping out a bitmap. Let's see. I think this is what we want. So we're going to end up comparing this image to this image after it's gone through this, back around. Run it? Okay. Okay. Oh, we were going to compare it. That's why we did that at the line. Okay, so 4.95, 10.7. Okay, so we get a little bit less RGBs. We get the same number of indices. We get fewer diffs. We pick up more less luma. Less diffs, less luma. We have to use more RGB. Okay, so that's actually not bad. If we don't do the wrapping on the encoding side, I don't think it costs us that much. So let's check the image is correct. So let's bring that up. Bring up GIMP. There we go. So here's the original. We turned that into QOI and turned that QOI into bitmap. And they look perfect. Okay, so it's working. Now, the size difference between mine and the reference implementations, 1486, wait, test card, 257 kilobytes. No, that's the bitmap. 24 kilobytes, as opposed to their 24 kilobytes. So it's actually not that big of a size difference. I'm curious though, can we make it better with that little bit of wrapping we can add in? Do we know how to easily add in? The easiest part of that is in can diff modulus 256. That actually solves most of the wrapping cases. Yes, blah, blah, blah. Not all of them, mind you. That's that. Okay, compared to last time, we're still getting the same number. 4902, 1205, 1898, 4216. Because you're not required to do the smallest thing. Now, we're doing a few less diffs, a few less lumas. Oh, wait. 8252. So how did adding a little bit of wrapping not help it? Okay, so I need to think more about wrapping so I can catch more conditions. So our valid values are -2, -1, 0, and 1. Those are all the diffs we can have. And that's straightforward in most cases. B is all previous. Let's see, let's just change it. Previous current. A dot becomes current dot. B dot becomes previous dot. This will be a little bit easier to understand. QOI file is, theirs is 24 minus 24. So if I go to properties, 24,397, the original. So I am literally just like a couple hundred bytes off because of those corner cases. How hard do I want to fight this? But I have time. We have time to try and figure this piece out. If we can get the wrapping done, then we should be good. And once we solve it for one of these cases, the rest is history. So if we take previous plus delta equals the current. So, you know, this could be dot R and R delta. It doesn't matter. This is the same for all of them. And it wraps. We have to care about wrapping. The cases where this happens, if -2 rev -2 equals current -1, 0 does not wrap, so I don't have to worry about that. And +1 equals current. These are the three cases we actually care about. If we subtract, we can't wrap the other way. It has to wrap this way. Therefore, current can only possibly be 255, 254, 255. And previous can only be 0, 1, 2. 2 minus 2 is 0, so that's not true. 254. So if I'm at 0, I subtract 1, I go to 255, subtract another one, I'm at 254. If I'm at 1, I subtract 2, I go to 250. I go to 0, then 255. If my previous is 0 plus minus 1, that'll get me to 255. And anything else doesn't matter. And lastly, if we're at 255 and we add 1, that brings us to 0. So current minus previous gives me 254, 254, 255. I mean, do I just look for these values? Because this is what we want in the end. These are the cases we're not catching by ignoring the wrapping. But it's enough that it saves us a few hundred bytes in a small file. Because right now our format is, well, it's in the range from -2 to 1 inclusive. We're trying to compute a delta. If we subtract, there are cases so if this was the case, then what we would really be seeing is current minus previous, which is 254. We would see 254. We would see current minus previous would be 255. Current minus previous would be -255. Are there other ways to get 254 that are legitimate? If one was 255 down to 1? If it's 254 and previous is 0, 1, or 0. $255. So what's the, I don't want to do a whole bunch of if statements for each color here. There has to be a way to do wrapped subtraction. Integer distance with wrapping?
You made it out. Those aren't your cookies. If you want something, you have to ask. You know that. You don't just get to get snake things whenever you want them. Right?
Not helpful. I don't want to do a battalion of special cases, though. And we could just say if current equals 254 and previous equals 0, er equals -2. I don't like this. It's 255 and previous equals 0 equals 1. 255 and previous equals 0, then it's -1. Current equals 0 and previous equals 255. I really don't like this. Let's just throw it in for now. Even if we don't like it, it may be good enough. DRDG 1, 2, 3, 4. DRDB 1, 2, 3, 4. Let's just try it. Brute force. Right. Oh. When in doubt, just brute force the sucker. That's not what I said to do. I said do that. Not green. And this actually isn't the part we really care about performance anyways, but I don't like it. I feel like there's probably some clever arithmetic trick. All right, our diff. We've got them all. Which means our two file image sizes. Let's see, this is the one that I want to emulate. This is one I want to match it. Oh, we have matched size almost. We are losing 8 bytes. because of Luma. 1902, 1898. 8 bytes, because our Luma doesn't wrap. And as much as I would love it to wrap, I haven't found a convenient way to not brute force this thing. Around the end with wrapping. Are any experts in my chat about weird integer wrapped arithmetic? Should be something a little bit easier. If we take our previous, we know what our min is. Let's see, min, what's here? So that's basically this here. Kind of need two deltas. One is the delta if we go around the long way. The other is the delta if we go around the short way. Well, if we go around the normal way. So if we go, maybe this is the thing. Let's try a little timeline here. So from 0, 1, 2, 3, 4, to 53, 254, 255. That's our set of numbers. And what we want to know is how far is it to go this way is when we subtract. Right, so if we want to go from 254 to 253, we just subtract them, and that's this distance. But if we want to go around the other way, we have to ask ourselves, what's the shortest distance that way? So we take 256 minus current plus our previous. Let me think this through. If our current is here, and if our previous is there, then we can subtract current minus previous and get the distance of 1. But if we want to go around the other way, it's 255. So 256 minus current would be 2. 2 plus this would be 255. I think this is the other distance. Int dr equals We will keep this around as bad as it is for a moment. DR1, DR2. G1, G, and G. Blue 1. Blue, blue, blue. Now, if this or if 2 is between that range, 2, 2. As long as one of them is in that range, I think we might be good to go. Oops. Green, green, blue, blue. And diff, that's the one we're looking for. Huh. But we weren't doing any wrapping here. We literally just took the difference plus 2. Why aren't we wrapping here? We support it on our decoder. Maybe we just not care about the extra few bytes. Where are we at? 510. Is there something lucky about this? Just don't worry about the wrapping. Let's do this. Let's just copy this work out. Maybe it will pay off in the future. And then we just comment that out. Now, PR. We don't check for wrapping. DG. DB. Let me simplify these back down. All right, I guess we just Luma and Diff without regard to the wrapping. We ignore wrapping, I guess. Last, let's see here. Test QOI. Maybe I should look at the example implementation. That might be the easiest way to detect wrapping, is to see what bit tricks he's using. Okay, we run the whole thing. And what do we get? We say that our diffs, we use a few less diffs, we use a few less lumas. But we do catch most of them. 27. So we actually catch all of them here and all of the lumas here. So actually, this is really not bad. We've gotten 99% of the compression we need. Do I go look at his implementation? I've been not so far, so maybe it's time. Yeah, decode encode times are freakishly fast. Not freakishly, but super fast. Yeah, he has a whole bunch of examples. I'm gonna go look on GitHub. Just QOI.h, blah blah blah, synopsis. He's probably got some very clever things. This is literally just, okay, so when we encode, I want the encode. There it is. Blah, blah, blah. That is ops, that's fine. Mask 2, that's fine. Hash, I agree. Magic number, fine. Pixels, max, I don't really care about that. Right, I'm going to pause for another restroom break. I'm drinking a lot of water here. I shall return shortly. Okay, we're super close. I'm just looking at the implementation for encode. Maximum size, he allocates. Oh, okay. He writes out his magic numbers with his height, his channels, his color space. He grabs the pixels. Starts with his initial color and his previous color. Or his current color and his previous color. Run 0, yep. Length, channels. Okay. Okay, well, if they're equal, run plus plus, if it's 62 or the end does the thing. Otherwise, so he's doing that very similar. He's looking up the hash. Otherwise, so where's the diff? Here's the diff. So here's the code he does around the diff. Huh. This person may be somewhat more clever than I. I mean, the wrapping is a little bit clever because you only have two bits of diff allowed. So allowing it to wrap saves you a bit. Let's see. Delta R, delta G, delta B, VGR, VGB, if. Oh, I see what he's doing. Minus 2 to 1. But that doesn't detect the wrapping, does it? His example implementation does not detect the wrapping either. When he encodes it, it is not looking for wrapping. Huh. When he's doing the encoding, he does not do the wrapping. His structure here I do like better. He's clearly thought about it a little bit more than I have. Yeah, he's not doing the wrapping. Why would I do the wrapping? I mean, I guess good enough. Diff. Luma. Huh. Okay, well, his implementation does not have that stuff in it. So I guess we're done, right? I mean, it's only a couple hundred bytes, so I guess we're good. Journal. Okay, QOI encoding is working. Tested against examples, and due to wrapping, we don't get 100% of the compression as found in the example QOIs, but the reference implementation also does not detect the wrapping conditions when encoding. I guess that's kind of the bottom line here. Okay, 524. We have maybe enough time to do this. So let's. I don't want any of the QOI files in there, so let's ignore it. QOI encoding is done. Okay, lastly, bed PNGs. We've included source QOI HPP. Thank you. Process data. Here it is. This is not what we're doing anymore. We're not allocating new memory here. Compressed size equals size. It's certainly not true. So what we go to for our reference is this. Encode. Encode. So we have our data, we have our width, we have our height, and we pass in our compressed size. I think that's it. All we do is really return that. Are we ready? So here's a question then. When did we decide to use unsigned values for width, height, and size? Oh, man. but they should always be positive or 0. Those are kind of the only ways you can get them. Int width, uint 32 width. Height, int uint 32 height. Int size with uint 32 size. Int star size, uint 32 star size. Oops. Int star size, uint 32 star size. There we go. All right. C standard int. Okay. Count. Pixel index. Okay. So what we're looking to do now is cd tools bin dot slash embed PNGs cd back up. Holy smokes. Oh, wow. So the file data, so this is PNG compressed data, comes in at 7.5 megabytes of PNG file. We expand that out to the full expanded image data size, which is 63 megabytes, which we're trying to shrink. And we didn't get it down to a quarter, we got it down to 14%, so 9 megabytes fully embedded. Oh my gosh, that's awesome. Now, we're not decoding that on the flip side, but, you know, star dot warehouse.cpp. That brings our image warehouse down to 350,000 lines of code instead of 1 million. But we're running out of time, and I don't have time to do the next thing. There's a little bit more we have to do with this. Maybe we do that. Okay. So we were doing widths and heights. And the sizes. We need the size of the actual payload for this to work. So I'm sorry, I just got too many windows open, too many things open. I'm going to close up GIMP. I think we're done with that for now. And calculator. Okay, I'm just getting cluttered here. We've been grinding on this a little bit. So we have blah blah blah. we load decode the thing, we get our size, we get our compressed size. Now, one thing I don't know is m underscore sizes. Oh, we do. We do. M underscore sizes. We can get the size of our asset in bytes, and this is just going to work for us then. Except that this part here, whatever's stuffed into sizes is what gets written out. So, not that one, not that one, my size, this one, temp size. Okay. Compressed size. Image index, is that a thing we get? I guess just index equals compressed size. That's the last piece of this puzzle. On our full thing. Button center chalk. Yeah, it's tiny. Perfect. Then we run this thing. Okay, so let's go ahead and try and open up image warehouse. Let's see, source image warehouse.h. Blah blah blah. Image warehouse.cpp. It's a big file, but it's not that big anymore. It's only 40 megabytes. Great. Yeah, it's only 300,000 lines. What's the big deal? Okay. What we care about is none of this. All of our different sprite animations. We could encode those better probably in the future. We don't care about UVs right now. That's all been working and tested. Okay. This is a bunch of UV names, if I'm not mistaken. Oh, come on, Emacs. A little bit lame. Yeah, if we get that down to 9 megabytes, that's kind of ridiculous. I mean, about 10 megabytes. One-seventh the size. Get size. Ah, okay. Problem with these big files. There they are. So we just heard 4K. This thing says that's the raw data, not the compressed data. $18 bytes compressed. So this should be 18. Right? The size at this index should be that. Write the binary. Oh, that's the right binary. Compressed size. So where do I write this source? We're gonna do this whole thing a bit higher. Huh? Or is it? Sometimes the size equals this. Write the source. Count, just make sure we're still good. Image warehouse. Reload this file. We get our sizes right. That last one should be 18. It is. Okay, now we have our new sizes. And if I'm not mistaken, button chalk center is right here. And that's 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 bytes. Perfect. Journal. QOI encoding is fully into embed PNGs. Embed PNGs now encodes to QOI and stores the actual payload size. Done. Now, our program won't actually run correctly because we aren't processing the QOI on the flip side. So, QOI in embed PNGs and image warehouse needs a bit of plumbing on the texture usage side to be complete. Okay, so one thing we can do is what's it called? We can actually run this build anywhere, doesn't really matter. Clean release. So this will, it won't run. Oh, application sandbox, ridiculous. This will take a minute, but it won't take near as long as it used to. Image, yeah, that only took a couple of seconds for image warehouse. Nice. Sound warehouse still takes me a bit, but we're going to shrink that a little bit more as well. I think we're in good shape to be done coding next week. I think we would have been in good shape to be done coding this week, but I had a short day on, what day was that, Tuesday? Yeah. so much better. Not bad. 2 days for audio compression. So that build took 1743.57, 1743. Yeah, so we're back down there 2 minutes of compile time. There we go. Last change. And we can at least see how big our executable is. AL. Oops, that's not it. AL. Source builds release. Okay, so we are now 45 megabyte executable. Booyah. Not bad. Nice. Okay, so dash M1 documentation metrics in weekly. We're not gonna fill it all in, but you know, we can stub it out. 26. We know what today's date is. It's the 19th. This hash is this hash. And we don't need accurate times just yet. We're not going to run the stats right now, but we are going to stub it in 1, 0, 0. Boom. Okay. Journal. Release size. We just did that. Source build release. Oh. Not working. There's no way it will work today. Oh, so good. It's our last release size. It was 189 megabytes, and in 1 week, we've cut it in quarter or more. Let's see how much we've compressed our stuff. Granted, non-functioning. Yeah, we've shrunk our total image size down, or our total executable size by more than a quarter. That is respect for my players' resources. Look at that. We are not bad. We're pretty good at this game. Let's see here. The lumbing to use the QOI encoded data on the render side is not there, therefore the game is non-functioning at this time. Total executable shrinkage. 100 times %. We can truncate about there. Because yeah, 24%. Our executable is 25% of the size we started at on Monday. Oh yes, this is going to speed up everything. It's going to speed up our program load time, the Steam download time. This is great. 45 megabytes. Cool. Let's save that. Commit, amend, no edit. And there you have it. We are done with the work for the week. On Monday, we will plumb in the render side for QOI processing. We will further shrink our warehouse files. That's one more item on our task list. And then we're done with coding, except for bugs. That's it. So you have a wonderful evening. Monday, we will try to get this wrapped up, and I'll see you next week. Have a good weekend. Bye-bye.